All right, in this video, we are going to finish up through the end of page 7 and the exercises that are between here and there. Hopefully you've watched the previous video that got us as far as exercise 5, and this will just be a continuation of that, working with some molecules now instead of simply elements like we were doing in the previous video. So let's take a look at a question here on exercise 5. Juglone, a dye known for centuries, is produced from the husks of black walnuts. Natural herbicide that kills off competitive plants around a black walnut tree. That's super cool. That's just really interesting in general. But the question isn't getting into that. It's actually just talking about this particular molecule and asks us to first find the molar mass. Anytime you see molar mass, it's wondering how many grams per 1 mole. In other words, go to your periodic table and add that baby up. Okay, this is always from the periodic table. When you need a molar mass, right off the periodic table. So we need to add up C10. So we need 10 times carbon's mass. Go look at your periodic table. Hopefully you'll find carbon is 12.01 grams for every mole of carbon. We need 10 of those because this juglone molecule contains 10 carbons. All right, to that we need to add 6 times the hydrogen's mass. Take a look at your hydrogen's mass in the periodic table. Should see hydrogen at 1.008. We haven't used that one before this in a previous problem. So we'll look that one up, 1.008. And we need 3 oxygens. So we're going to add to that 3 times oxygen's mass, which is 16. Add those all together, you've got the molar mass of juglone. All right, let's get that added up. 10 times 12.01 plus 6 times 1.008 plus 3 times 16. Now, if you're one of those people that's doing that in your head and saying, I know 3 times 16 is 48, super, go ahead and punch that in. Juglone 174.148. 174.15 would be okay. Okay, that's our molar mass for juglone. And we're going to need that number more than likely in one of the questions that would follow here. And it does, in fact, come up in the very next question. They want to know how many moles, calculate the number of moles of juglone present in a sample that has a mass of 1.56 times 10 to the negative 2 grams. Again, don't duck the scientific notation. If you know you're a little less comfortable with it, work with it as much as you can, as often as you can on things that don't really matter. Okay, and not that homework doesn't matter, but it's not as high stakes as a test or a quiz or something. So when it's not as high stakes, try it and see if you can punch those in and get the right answers. Right? If you're comfortable with them already, then you're all set to go. All right. So we need to get that into moles. And as always, we need an equality statement of some kind to fit in that box. All right. We're going to use the one that we just figured out, and that is that 174.15 grams of juglone. Should be a 10 there. Are equal to 1 mole of that substance. Keep writing 10. I'm not sure why. Okay. Go to your calculator. 1.56 times 10 to the negative 2 divided by the answer we just got. Now, you can go ahead and type in 174.15. You can go in and bring that number down. You can go up and grab that number if you have a TI-84. It'll let you go up and grab that answer and insert it, like so. Not have to type it in again. That's genius. Yeah, that's what I would recommend you doing. Okay. Another way to do it, just so you know, this might be something that you already know about your calculator, but another way would have been to use the answer key. But now that I've gone on to another problem, the answer would now be the previous question's answer. I don't want that one. But in any case, the answer that we come up with here, displayed there on the screen, 8.96 times 10 to the negative 5 moles of juglone. C10, H6, 3. O3. There's our answer in moles. Boom. Conversion, we're the molecule instead of just an element. Straightforward mole to gram, or gram to mole conversion. You might think that's real simple, especially if you took first year chemistry. Like I've done 1,000 of those. You're right, and I'll tell you what, converting to moles is often worth a point on the AP exam in a free response question. So if you can do that and it's easy peasy, you're going to be all set for at least a few easy points on those questions that everybody should be able to get. All right, question 6, exercise 6. Very similar kind of question, or at least first for calcium carbonate's molar mass. So we're going to need to go add up calcium carbonate. Now in the AP exam, they're going to give you formulas for this. You wouldn't have to be able to take calcium carbonate and turn that into a formula. But hopefully if you were in first year and you really hammered out those nomenclature exercises that we made you do, you'd be able to come up with calcium carbonate. And some of the more common ions to get to know includes the carbonate ion, which you see is going to come up here, be mentioned later in the problem. CO3 with a -2 charge is that carbonate ion. You're going to see that one quite often throughout the course. Okay? So they want the molar mass again. So go to the periodic table and add this up. I need 1 calcium. Calcium on the periodic table, 40 let's just double check that. Here it is, 40.08. All right, that's calcium. We just need one of those since it's calcium. Carbonate contains just one, so 40.08. We need 1 carbon, that's 12.01. So there's my carbon. And we need 3 of those oxygens. Add that all up. Let's see, 40.08 plus 12.01 plus 3/16, or a 48 if you want to add it up that way. And our answer comes out to be 100.1 grams calcium carbonate. Now you might notice I'm rounding off a little bit. You could go 100.09. Our periodic table has 2 decimal places. 100.09 would be perfectly reasonable. The answer key on the bottom of the corner here says 100 exactly. I don't necessarily love that, but there's our answer anyhow. Okay. I'll mention one thing here, it's just a little detail, but don't get in the habit of having highlighters out, extra colors necessarily. Try to do as many homework problems and in quizzes and tests and labs as you can without extra colors and highlighters and things like that, because on the AP exam, which is part of what we're prepping you for with all this, in the AP exam, you're not allowed to use any highlighters or anything fancy. You're going to have a pencil, and that's it. All right, so don't get too comfortable with having to have a highlighter all the time. Try to work yourself away from that. I love that you help highlight your answers so I don't miss them, but I would recommend instead of doing that highlighting business, just go ahead and put a box around it. Save yourself that distraction of the color. Having to go to a separate tool wastes time, which isn't as big of a deal as the fact you're just not going to be able to have them on the day of the test. All right. Now, it says here a certain sample contains 4.86 moles of calcium carbonate. All right, calculate the mass in grams of this sample. All right, so that's our first part of it. We're going to convert that from moles into grams. Much like we did in the previous problem, we went from grams to moles. We're going to use the molar mass that we just calculated. And again, we know that then is an equality statement. You're not required to write these little equal signs in that I do for a little while longer. I won't do them forever. But whatever goes top and bottom in our box here, in the numerator and the denominator, should be an equality or some kind of a ratio that we know to be true for the question that we're on. And in this question, we know that 1 mole of calcium carbonate, we just added this up, has a mass of 100.1 grams. So I'm going to use that here. And notice what that does, of course. Moles, pardon me, moles will cancel out, and that'll leave us with grams. All right, so I go back to my calculator, 4.86 times 100.1. Gives us 486 grams of, let's label it, calcium carbonate. Okay, make sure to try to label those things as you're working your way through the problem. Now, the second part of it, don't miss that. The second part of it says calculate the mass of carbonate ions present. Okay, so this was the whole total mass of the whole samples here. On the second part of the question, they want us to go to just the carbonate ions. So that means pull out the carbon and the 3 oxygens and just figure out those. Well, for every 1 mole of calcium carbonate that we have, there's 1 mole of calcium, there's 1 mole of carbon, there are 3 moles of oxygens. That's what we added together initially, right? So if they want us to focus ourselves here on the carbonate, then all we need to do is add up the pieces that they're interested in. All right. So in this question, the part that we're curious about, the carbonate part of this, is the carbon and the 3 oxygens. Right. So we're going to go ahead and still, pardon me, I keep getting interrupted. We're going to go ahead and still take our 4.86 moles and convert that into grams, but we're not going to use the whole thing because for every mole of calcium carbonate, there's a carbon and 3 oxygens. So 4.86 moles of calcium carbonate contains, for every 1 mole of calcium carbonate, you can think about it this way, there's 1 mole of carbonate ion, right? So if we look at the formula there, for every 1 mole of calcium carbonate, there's a CO3 in there. For every 1 calcium carbonate, there's one of the carbonate part that we're most interested in. There it is, within the hole is that part, right? So we're kind of taking our calcium carbonate and we're zooming in on the part that we're most interested in. In that compound, it's the CO3. And for every 1 mole of CO3, it has a mass of its own. And that's just going to be the carbon and the 3 oxygens. So let's go back to the calculator and add those up. Carbon would be 12.01. And 3 oxygens would be 16s, 3 of them. So the carbon and the 3 oxygens make a total mass of 60.01 grams. So I've just added up the parts that we're interested in this problem. So as far as my calculation is concerned, 4.86 times 60.01 gives us an answer of 291.6, or significant figures and rounding would say 292 grams of just carbonate ion that the second part of that question asked about. So there's that part, and our second part of 6B. All right. There will be a lot of questions in different places throughout the course where you're given a compound and you're asked to focus in on one part of it. In this case, we were given calcium carbonate, and we're asked to focus just on the carbonate aspect, the carbonate ions that are present in that compound. They're going to be coming from a different reaction, perhaps. This might have been the result of a reaction in a different question, but we want to be able to extract or just sort of focus our attention on the part of the compound that the question's asking us to look at. Here we leave the calcium out, as if that's not an important part of what's going on in the second part of 6B. All right, let's look at 7. Number 7 mentions a compound called isopentyl acetate, which is the flavor of the smell, rather, of bananas. I remember a lab in college when we produced this molecule, and the lab smelled like bananas, and it was just spectacular. Just an amazing smell. It says here, bees, interestingly, release a small amount, 1 microgram, of this compound when they sting. So apparently it's not real pleasant under your skin. The resulting scent it's not even the stinging agent, turns out. The resulting scent attracts other bees to join the attack. So those rotten buggers bringing in more of their friends by releasing the smell of bananas. We've been betrayed by bananas if you're ever attacked by a swarm of bees, which when I was younger was one of my great fears. I read about killer bees when I was in grade school and scared the bejesus out of me. Ever since then, killer bees freak me out just a little bit. Fortunately, I live in North Dakota, where it's too dang cold most of the year for killer bees to survive. So, it says here, let's figure out the number of molecules released in a typical bee sting. So that's from this amount right here. Now, we're not going to use the micrograms part. You wouldn't have to know how to get from micrograms to grams. They're going to give it to you here. 1 times 10 to the negative 6th, in other words, a millionth of a gram. We're going to use that number to start out. 1 times 10 to the negative 6 grams of isopentyl acetate. In a problem like this, you could write out the formula, C7H14O2. You could just write IPA if you wanted to write that, or just IA for isopentyl acetate, some kind of abbreviation. As long as you know what it is, especially in a question like this where there isn't any other compounds involved, any abbreviation you use would probably be okay. Now we need to get that from grams to molecules. So remember, we're going to go from grams to moles, because everywhere you are, you can get to moles relatively easily. And then from moles, we'll go on to molecules, which is one of those particles like atoms that we talk about. So this is going to be a 2-step conversion. All right, 1 mole of our IPA, or isopentyl acetate, has a mass of some number of grams of that C7H14O2. So we need to go to our periodic table and add these up. All right, we're going to need 7 carbons, so that's 7 times 12.01. We're going to need 14 hydrogens. Those are 1.008 apiece. And again, if you don't have these numbers memorized, don't worry about it. They're on your periodic table, which you always get to use. So just have them, look them up. And then we need 2 oxygens. That's 16 apiece. Total mass for isopentyl acetate, 130.18. I'm going to go ahead with that right there. Now that doesn't get me to molecules, so I'm going to need to add a second step on the end of this question, or this work. And in that part, we're going to say that 1 mole of our compound is 6.02 times 10 to the 23rd. Remember, that's Avogadro's number. That's on your formulas page. Molecules of our isopentyl acetate. So go to the calculator. 1 times 10 to the negative 6 times 1 divided by 130.18 times 6.02 times 10 to the 23rd. And my answer here comes out to be 4.6 times 10 to the 15th. Now notice, the original value that they gave us here was 1 times 10 to the negative 6. Because that 1 here has one significant figure, okay, only one SF, one significant figure, that's really poor. It's really rounded off. It's really, really not precise. And so for that reason, our answer can't be more precise than that. So we have to actually round off that nice number from my calculator over there to 5 times 10 to the 15th molecules. You can't have a more precise answer, remember, than any one of the weak numbers that you used in finding your answer. So we have to round it all the way off to 5. And it's kind of an approximate number anyway. A given B may release slightly more or less than 1 microgram, so around 5 times 10 to the 15th is accurate enough. How many carbon atoms are present in that amount of isopentyl acetate is what question B is going to ask. So I'm going to take my 5 times 10 to the 15th molecules of C7H14O2. And in that compound, for every one molecule, there are 7 carbon atoms, right? If I look at the formula, I can see that there. C7H14O2. So for every one molecule of C7H14O2, right, there are 7 carbon atoms. We can see them hiding out there in the formula, right? There's my C7 right there. So 7 times as many carbon atoms as there are molecules. Kind of like, let's say in every one human, there are 10 fingers. Or in every one human, there are, gosh, I hope it's right, 7 cervical vertebrae. No, there might be more than 7. I think there's way more than 7. So take that back. In any case, 5 times 10 to the 15th. So I'm going to go to my calculator. 5 times 10 to the 15th times 7. Gives me 3.5 times, 3.5 times 10 to the 16th. Now you'll see there in the answer it's rounded off again because we only have one significant figure. We're going to round that off to say 4 times 10 to the 16th carbon atoms. Okay, boom. There we are. So that's exercise 7. Now, you'll notice here in the next little section of the notes on this page, it talks about some compound, or rather elements that exist as molecules. And they're specifically here the diatomic molecules. These are molecules that exist paired up, 2 atoms of the same thing put together. So you're going to see those quite often in various equations throughout the year, but it's only the case when they exist as elements. So hydrogen, nitrogen, oxygen, you see those listed here. Hydrogen, nitrogen, oxygen, and the halogens. And the notes here refer to them as the gens. Okay? Hydrogen, oxygen, nitrogen, and the halogens, which remember are group 17. And what it's telling us here, and I'm not exactly sure why this is inserted here in the notes, but it's something that you hopefully remember from first year chemistry if you took that course. What it means is in an equation, hydrogen gas, if I had hydrogen gas, say, generating it in a lab reaction, or if I was using it in a fuel cell or something, hydrogen gas comes in pairs. Hydrogen gas is H2. Oxygen gas that you're breathing right now is O2. It's not just O's when you're breathing oxygen in the air. Nitrogen is not just nitrogen. And so when you see it in the reaction equation, you might see it in 2's. I'm not sure why that's inserted right here. It's not necessarily that important to what we're working on in this question, but it's here anyhow. All right, in the last section of this part of the stoichiometry packet, talks about percent composition. And basically what this does is it takes a compound, like in this example here, ethanol, and it lets us examine what part of that compound is carbon, is hydrogen, is oxygen. Ethanol is made up of those three elements. Most compounds are made up of multiple elements, of course, and so we should be able to look at them and figure out what part of the compound comes from each of those. Why that's important is different for each compound. It's different in different parts of the course. There'll definitely be places where you need to be able to figure out quickly how much of a particular compound is due to each element. So thinking about the compound as sort of like a pie chart or as a whole, and you see that mentioned here, what part of a whole comes from each element? Carbon, hydrogen, and oxygen in this example of ethanol, okay, each contribute to the pie, each contribute to the total. And when we added up those molar masses just a minute ago on some of these previous compounds, you could see easily that some of the elements were a much larger part of the pie than others. So for example, when we first went through, let's see here, our juglone, we could see that of the 174.15 for juglone, 10 times 12, right? And it doesn't take a math major to know that 10 times 12, that's about 120. That's a lot of the total 174 that's coming from the carbon. And so as we look at our compound, each element contributes a little bit of the pie. Carbon would be a large chunk of the pie. Oxygens contributed 48. That's a pretty big chunk of it. The hydrogens only contributed about 6. And so as we add those all up, we get our total of 174. But obviously carbon is the largest part of the pie chart, or the pie. Oxygen is the second part, and then hydrogen just a tiny little piece of it, as far as what part of the overall mass each of those contributes. Okay, so what we're looking at then is that even though a compound may contain 3 or more elements, it's not always obvious, even as looking at the formula, as to what part of that compound's mass is the result of each compound or each element within the compound. This example takes us into ethanol and shows us how we would add up that molar mass. Here's for carbon, 2 times 12.01, and there's that 24 for carbon. 6 times hydrogen's mass of 1 gives us a mass of around 6. And then oxygen, we have 1 of those in ethanol times 16, total of 16. So even looking at this, you can see that out of a total of 46, carbon is the biggest share of that 46, a little more than half. Oxygen is a fairly large part of it, about a third of it. And then hydrogen is just a small piece of the pie. And then we can figure out percentage-wise how much of that compound's mass comes from each of those elements. That's what percent composition lets us do. And the calculation that they show in an example here is we take the part and put it over the whole. So the part is from one of the elements divided by the whole, which is the mass of the total. This is no different than if I said what percent of our high school's population is sophomores on a given day. We would take sophomores divided by the total number of students in the building times 100, and we'd have a percentage. About a fourth, probably a little bit more than that, of our students would be sophomores. So for example, any percentage that you do can be done the same way as mass percentage can be done here. So we're looking in our next example here at a compound called Carbone. So Carbone is a substance, it says here, that occurs in 2 different arrangements, but have the same formula. And that formula is important because that's going to give us our molar mass. C10H14O. That's a big old molecule. Okay. So as we look at it here, that's going to be our formula overall with a total molar mass. It says here one type of Carbone gives caraway seeds their smell. The other is responsible for the smell of spearmint oil. So it's interesting that one molecule, different structures, gives us this very different smells. Calculate the mass percent of each element in Carbone. There's our prompt, really. Pardon me, it slipped on me. There's our prompt. Calculate the mass percent of each element. So we need carbon, hydrogen, and oxygen. We'll need 3 different answers. The key for all of these then, we need to have a calculation for each element since we're being asked for all 3. But in each case, we're going to use the part over the whole. Part over the whole. Part over the whole. And we need that whole mass right away. So let's go to our calculator and add up C10H14O. You wouldn't necessarily need to show what you're adding up, but you definitely would need to add it up and put those numbers in to our denominator. That whole point here, in that little example above, the whole mass includes all of those atoms put together. So let's go add those up. We need 10 carbons, so that's 10 times 12.01. it's 14 hydrogens, so 14 times 1.008, and oxygen just 1, so that's a 16, for a total of 150.212. Now, if you get that denominator wrong, oh boy, you're going to get them all wrong. So be really careful that in the end, you haven't done the denominator wrong. Double check your work. Make sure that you got everything right. So I'm just going to look here at my math. 10 times 12, that's carbon. 14 times hydrogen, and 116 for oxygen. That looks good. Okay. So on the top, we'll go the carbons. That's 10 times 12. On the hydrogen, 14 times 1.008. And for the oxygen, simply 16. And for each of these, since we want a percentage, as is almost always the case, when calculating percentage, you'll take it times 100. Okay? So each of those times 100 will give us a percentage, percent carbon, percent hydrogen, and percent oxygen. Now, calculation 10. Actually, tell you what, I'm going to use that number several times. So I'm going to bring that number, and I'm going to store it as X. You wouldn't have to do that, but I'm going to store that in my calculator as X. And if you don't have the ability to do that, or if you don't know how to do that, just have to type in 150.212 each time. But I'm going to store that as X in my calculator since I want to use it over and over again and not have to type it in every time. Saves me time, saves me risking a typo. So 10 times 12.01 for my carbons, divided by X, divided by that 150.21 that I stored. And then I take that times 100, that's going to give me a 79.9%. Actually rounds off to 80.0%. Okay. Now my calculation here in my periodic table, I guess I could go a little more on significant figures. Because we have 4 significant figures here, my answer could have 4 significant figures. So 79.95%. For my hydrogen, we're going to go back to the calculator and say 14 times the hydrogen's mass, 1.008. Again, divided by my total, which I stored as X. That's going to give me times 100, 9.394. I actually get 5% when I round mine off. And then for the oxygen, 16 divided by the stored X value again. And that times 100 would give me 10.65%. Okay. Now I didn't show in my calculator the times 100. You can do that. I was just moving that decimal over twice. But for example, on the oxygen there, times 100 would give me a percentage of 10.65. Now you can always double check these at the end because if you did everything right, these should total what? Hopefully you said 100%. Because all of the mass needs to be accounted for. It should round off pretty dang close to 100%. So let's just quick double check. It doesn't hurt to do that. Oops, 79.95 plus 9.395 plus 10.65. Total, 99.995. That's close enough. So, Exercise 9 does very much the same, but for a different molecule. This is C14H20N2SO4. Holy smokes, right? That's the formula they say here for penicillin F, which is a form of penicillin. Pretty important molecule. You study history, pretty big deal. Penicillin, which has been turned into many, many similar sort of antibiotics with many different similar names that you may have taken in your life at some point. Now, notice this has 5 different elements: carbon, hydrogen, nitrogen, sulfur, and oxygen. So be very careful in adding those up. Tell you what I'm going to do. I'm going to let you solve this one. You've got the answers here on the screen, right? I've got them sort of in my corner. I don't think your copy maybe has that, but take a look at it. You could just freeze the frame here and have those answers there, or just slide back to them in a moment. Check that you can get those answers. All I'm going to do with you here, and then I'm going to end this video, is make sure we can add that mass up properly. So tell you what you do. Take a minute, pause me, and then we're going to add up that C14H20N2SO4 off the periodic table and see if you don't get the answer that I get. All right. So pause me while I add that up and see if you can get it to add up the same. And that's going to be your denominator in every one of those 5 calculations. That's kind of an important deal. So go ahead and pause me while I finish adding this up. I got a mass of 312.36. That should be my denominator. I'm just going to make sure I didn't make any mistakes here. Let's see. I've got 4 oxygens. I've got a sulfur in there. I've got 2 nitrogens. I've got 20 hydrogens and 14. That looks right. So hopefully we got an answer of 312.36. That's going to be your denominator for all 5 of those. You're going to do 5 separate calculations for carbon, hydrogen, nitrogen, sulfur, and oxygen. And again, see if you don't get these percentages that are stored here in the corner of our box. See if you get those answers. And then if you have trouble with those, go back and just make sure you haven't typed something wrong into your calculator. These aren't very difficult calculations. I won't begrudge you watching me work through those, but see if you can't get those answers to work out. And we're going to call it a day on this video. We got through problem number exercise 9 on page 7, and our next video will pick it up from there. Thanks so much. Keep up the good work, and I'll talk to you soon.